Hello everyone. Let us discuss today EUTRA and NR multi-connectivity options. And these are the references from 3GPP I have mentioned from which I have taken this content. So let us start. This is the content of this video. Introduction to MRDC. We'll be discussing about MRDC control plane and user plane in terms of MCG, SCG and split bearer. Single uplink transmission, very important topic, and band combination for ENDC as specified by 3GPP. Here we will discuss example of ENDC, but you can refer 3GPP for further NEDC and NRDC cases. I'm sure you might have heard these terms many times: MRDC, ENDC, NEDC, NGENDC. So let us start with MRDC, and by the time we finish, we will conclude with all these DC or dual connectivity. So on your screen, you can see that this is the definition as per 3GPP. This definition is for MRDC, which is multi-radio dual connectivity. Many places it is also mentioned as multi-rad dual connectivity, but I have not seen any 3GPP document mentioning it as multi-rad dual connectivity. So I will consider this as multi-radio dual connectivity. Coming to definition part, I will add some portion of this definition for the sake of simplicity. So now let us understand what is MRDC. So as per this content, MRDC is dual connectivity where a multiple RxTX UE, multiple RxTX UE means a UE which can transmit or receive multiple frequencies simultaneously, may be configured to utilize resources provided by two different nodes which are connected via non-ideal backhaul. Okay, one providing NR access and other one providing either EUTRA or NR access. So point to note here is that one node is mandatory to provide NR access, means via one node we need to access the NR 5G radio interface, and from the other node it can either be EUTRA-LTE air interface or 5G radio interface. One act as the MN. MN is master node. Master node is one which has control plane connectivity towards core, and other act as SN, secondary node. So in this example, we are considering this G node B as master node, but there can be several other use cases where master node B can be considered as E node B. So we will be discussing those on subsequent slides. Coming back to definition, the MN and SN or the master node and SN node are connected via network interface. So these two are connected via network interface, and at least the MN is connected to the core network. At least MN is connected towards core network, and core network can be either 5G core or it can be LTE core. So this is multi-radio dual connectivity or MRDC as per 3GPP. Now based on this definition, there can be two type of MRDC. First, MRDC with EPC, where master node is connected towards 4G core, and second can be MRDC with 5GC, or where master node is connected with 5G core. So we'll be discussing that in subsequent slides. Now let us see one by one each type of MRDC. So MRDC, when EPC is connected, it is MRDC with EPC. Second is MRDC with 5GC when core is 5G core. MRDC with EPC, we have ENDC, which is EUTRA-NR dual connectivity. So let us see by it an example. So EUTRAN supports MRDC via ENDC or EUTRA-NR dual connectivity, in which a UE is connected to one E node B, and this E node B acts as master node or MN, and one G node B which acts as SN, secondary node. The E node B is connected to the EPC or 4G core via S1 interface, and E node B is connected to G node B via X2 interface. The G node B might also be connected to the EPC via the S1U interface, user plane interface, and other G node Bs with the X2U interface. So C plane connectivity towards core can be only from one node, and in case of EUTRA-NR dual connectivity or ENDC, it will be from E node B side. Let us see other options when MRDC is with 5GC. So when MRDC is with 5GC, we have first one as NGENDC, or NG stands for NGRAN EUTRA-NR dual connectivity. So NGRAN EUTRA-NR dual connectivity is when a UE is connected to one E node B, and it is NG E node B, means next generation E node B, which can be connected to 5G core. So these kind of E node Bs are called as next generation E node B or NG E node B. That is why in the name you can see it is NGENDC. So coming back, in which a UE is connected to one NG E node B, which acts as master node. Master node is NG E node B, and one G node B, this acts as secondary node. The NG node B is connected to the 5G core, and G node B is connected to NG E node B via the EXN interface. Remember, the node which acts as master node, that node name will come first. Here E node B is the master node because control plane connectivity towards core is via E node B. That is why first name in this kind of multi-radio dual connectivity nomenclature will come of E node B. So for our case it is NGE, which is NGRAN EUTRA, and N for NR dual connectivity. Now there is one more option in MRDC with 5GC, which is called as NEDC or NR EUTRA dual connectivity. So in name NR is coming first. So as discussed, this means that master node will be the G node B, and master node is the one which is connected towards 5G core. So NGRAN supports NR EUTRA dual connectivity or NEDC, in which a UE is connected to one G node B, which acts as master node, and one NG E node B, which acts as SN. The G node B is connected to 5GC, and the NG node B is connected to G node B via EXN interface. There is one more option in MRDC with 5GC, which we call as NRDC. In this kind of connectivity, we have NR-NR dual connectivity. In this, a UE is connected to one G node B that acts as MN, and other G node B that acts as SN. So point to note here is both the nodes are G node B, 5G nodes. There is no E node B. The master G node B is connected to the 5G core via NG interface. This is NG interface, and to the secondary G node B via XN interface. The secondary G node B might also be connected to 5G core, but only with NG-U interface, means NG user plane interface. So I think now this clears the confusion. So first we have type of dual connectivity. Dual connectivity as a whole is called as multi-radio dual connectivity. Then based on the type of core used, it can be divided into two parts: MRDC with EPC if 4G core is used, and MRDC with 5GC if 5G core is used. In MRDC with EPC, we have only one option, which is called as ENDC or EUTRA-NR but in case of MRDC with 5G core, we can have three options: NGENDC, NEDC, and NRDC. Let us discuss MRDC control plane. This figure is of control plane architecture, ENDC the left side, and for MRDC the right side. MRDC with 5G core, the right side. So RRC layer, as we all know that RRC layer operates between the BTS and UE, and it transfer messages belonging to the RRC signaling protocol. In MRDC, the UE has a single RRC state, means it can be either RRC inactive, either RRC connected, or RRC idle based on only one node, which is master node, based on the MNRRC, and a single C-plane connection towards the core network that we have already discussed. For NDC, control plane towards core is connected via E node B as shown here, and for MRDC with 5G core, it can be any node. It can be 5G node or LT node depending on the configuration. As we have seen that there can be three type of configuration. Each radio node has its own RRC entity. It can be EUTRA version if the node is an E node B, or NR version if the node is a G node B, and it can generate RRC PDUs to be sent to the UE. RRC PDUs generated by the SN can be transported via the MN to the UE because RRC state is only with respect to MN. So what all RRC PDUs need to be transmitted towards UE from secondary node follows the path from primary node. They will come to primary node, secondary node will send it to primary node or the master node, and then master node send it towards UE. As we saw in previous slides that RRC PDUs generated by the SN can be transported via the MN to the UE, as this figure was telling. But this process is time taking and may not be helpful in scenarios which requires urgent action like mobility related cases, handover related cases. So SRB3 is introduced to reduce the latency of RRC signaling between secondary node and UE. So as a UE can configure SRB3 if the SN is G node B. It can only be configured if SN is G node B. Which all cases we have SN G node B? ENDC, NGENDC, and NRDC. All these cases are having secondary node as G node B. SRB3 enables RRC PDUs for the secondary node to be sent directly between the UE and the SN. So if UE is configured with SRB3, it can send some of the controlling message or RRC PDUs towards UE directly. It need not to be sent via E node B. And when it happens only when this special type of SRB3 is configured. So SRB3 in downlink can send RRC reconfiguration. SRB3 can be used in uplink to send RRC reconfiguration complete and measurement report. So have you guys heard about SRB4 and SRB5? Let me know in the comments if you know what is SRB4 and 5. And first person will get chocolate from me. Now let us try to understand user plane. Here we are focusing user plane of MRDC with EPC or ENDC scenario. So ENDC can have three type of bearers. First one is MCG or master cell group bearer. So a master cell group bearer uses the RLC MAC and physical layers within the master node. Means it uses the 4G implementation and 4G air interface. The PDCP layer can be configured to operate either in 4G or 5G mode. Note, here we are saying 4G or 5G mode of PDCP layer or 4G or 5G version of PDCP layer. Even LTE Node B is capable of configuring 5G version of PDCP layer. Now, when to use 4G version of PDCP and when to use 5G version of PDCP, it depends on the type of services we are using. Some services may be benefited from 4G PDCP version and another can be benefit from 5G PDCP version. Let us try to understand it via example. So 4G version of PDCP supports minimum of 7-bit sequence number, while 5G version of PDCP supports minimum of 12-bit sequence number. So for the voice services, it would be useful to use 4G PDCP, as doing so will reduce the PDCP overheads because it has less bit sequence number. So voice bearers can be kept on the 4G network and use 4G radio. But for data bearer, overhead generated by PDCP sequence number is very low. If we see in terms of percentage of overall packet size, data bearers will have larger packets to send. Also, large set of PDCP sequence numbers are required when using high throughput application. So to avoid the issues associated with sequence number ambiguity, the user plane bearers transferring data content may be allocated an MCG bearer using the 5G PDCP layer. Now, how can we recognize whether a bearer is MCG or SCG bearer? So MCG bearer can be recognized using RLC, means a type of bearer can be recognized seeing the where is the RLC falling for that bearer. So for our this bearer, RLC is in MCG. So this bearer is MCG bearer. Now there can be two type of bearers, whether MN terminated or SN terminated. So if we want to see how which kind of termination bearer is, we need to look at the PDCP. MN terminated bearer is the bearer for which PDCP is located in the master node. So in our example, this one is the MN terminated bearer and this is the SN terminated bearer, because PDCP for this bearer is located in the secondary node. So this was all about MCG bearer or master cell group bearer. We also discussed about how to recognize whether bearer is MCG or SCG, and it is done based on RLC layer. If RLC layer is in MCG, it is MCG bearer, and if RLC layer is in SCG, it is SCG bearer. SCG bearer we will be discussing in the next slide. Now let us discuss about SCG bearer or secondary cell group bearer. So as we can see that RLC is located in the secondary node. This bearer is SCG bearer. An SCG bearer uses the RLC, MAC and physical layers within secondary node. That is, it uses a 5G implementation of these layers and 5G air interface. SCG bearer always use the 5G version of the PDCP, irrespective of the master or secondary node. Which kind of node use, whether G node be used or E node be used, PDCP layer is always 5G version. Can you guess which one of these is MN terminated bearer? Yes, this one is the MN terminated bearer, and this bearer is SN terminated, as it is identified by PDCP layer. So just to summarize again, type of bearer, whether it is MCG or SCG, will be based on the RLC layer. And when we want to identify if bearer is MN terminated or SN terminated, we identify using PDCP layer. So this is the split bearer, the third one and the last one. As seen in the slides, split bearer always use 5G version of PDCP, and it can use both the 4G and 5G version of RLC MAC and physical layer. Means it can use 4G and 5G, both the air interfaces. Any guesses why it is called split bearer? Because for this bearer, data transmission path is split over two air interfaces, 4G and 5G. So for split bearers, both MCG and SCG radio resources are involved. Continuing our discussion of split bearer, this is the most common implementation of split bearer I have seen in the networks, where PDCP is used from G node B and data is splitted at NR PDCP 1 towards 5G lower layers, which reaches to UE via 5G air interface, and second split is towards 4G lower layers, which reaches UE via 4G air interface. So from core network, data is transmitted to 5G PDCP or NR PDCP, and then NR PDCP split it towards 4G and 5G lower layers, which ultimately reaches UE via 4G air interface and 5G interface. Now, decisions like when to split the data and whether to split data only for a few specific bearers and how much data should be routed towards each BTS 4G and 5G, all these can be defined by vendor specific flow control algorithm. Any guesses which type of bearer is this? This one? Yes, this is SN terminated, SN terminated SCG bearer. And this one, this is SN terminated. PDCP is in SN and MCG bearer because RLC and other lower layers are in MCG. For split bearers, MN terminated SCG bearers and SN terminated MCG bearers, PDCP data is transferred between MN and SN via the MN-SN user plane interface. So as we have seen in this example, like for our case, SN terminated MCG bearer, we need to transfer the data between MN and SN. So it is done via user plane interface. So in this case, it is X to U interface. Let us see the nomenclature of the interfaces. So first example is for U plane connectivity for ENDC. When our core network is LTE, then connection between ME node B and ENG node B is called as X to U, and the connection between ME node B and SGW or ENG node B and SGW is called as S1U interface. Similarly, in case of MRDC with 5GC, when core is 5G, then interface between MN and SN, user plane interface between MN and SN is called as XNU interface, while the interface between UPF and MN or SN is called as NGU interface. Let us have a look at C-plane connectivity. For ENDC, when core is 4G, the C-plane interface between ME node B and ENG node B is called as X2C interface, and the interface between MME and ME node B is called as S1 MME interface. For MRDC with 5GC, when core is 5G, the interface between MN and SN is XNC interface, and interface between AMF and MN is NGC interface. Single uplink transmission is very important topic regarding UE capability and also band combination used in ENDC. So as we know, UE which supports ENDC should be capable of transmitting uplink data simultaneously across 4G and 5G air interface. But here is a catch. A UE with true transmitters can generate intermodulation products or intermodulation interference. For the sake of time, we will not discuss about intermodulation interference in details here. But if you want to know more about intermodulation interference, you can comment and tell me. I'll try to make a short video on this. So for now, remember, whenever a transmitter transmits two frequencies, it generates intermodulation products, means it transmits some more frequencies other than it is intended to. So we'll try to understand this with an example. Here consider, because UE is in ENDC mode, it is connected to E node B and G node B, where E node B is configured with band 1 FDD and it is using 1920 to 1980 megahertz as uplink frequency and 2110 to 2170 megahertz in downlink. While for G node B, it is configured with band 77 TDD, which is having frequency from 3300 to 4200 megahertz. Let us plot these frequencies as here. So this is LT, these frequencies 1920 to 1980, and here this band is 2110 to 2170, and likewise for 5G. Now let us try to calculate the intermodulation product for this. How we can do it? Let us do it via making F2 minus F1. So if we are subtracting 1980 from 3300, means 3300 minus 1980, it is giving us 1320 megahertz. And if we subtract 1920 from 4200, it gives us 20 to 80 megahertz. So between this band from 1320 megahertz to 20 to 80 megahertz, this transmitter, our UE, can generate intermodulation interference. Problem will be for this particular area, because UE is transmitting in uplink 1920 to 1980 and from 3300 to 4200 simultaneously, but it is also generating frequencies in this band, and which is coinciding with the downlink. So UE is generating interference for its own downlink receiver while transmitting two bands in uplink. So I hope this make you understand about intermodulation interference scenario, which can occur more often in ENDC, but it is not that every band combination of the LT and NR will generate coinciding intermodulation product. So based on this, 3GPP decides which band combination can be used. And UE can support all the bands defined by 3GPP or some of them. UE indicates the single uplink transmission capability via single uplink transmission information element. So this is the information element is sent by UE. Here in this, UE can tell which all band combination it supports for ENDC. Now let us have a look at band combinations defined by 3GPP. As we have discussed that there can be few band combinations allowed to rule out the possibility of intermodulation interference. So 3GPP has mainly defined intraband FR1 and interband combination. Under intraband FR1, it can be contiguous, means FR1 band used for LTE and FR1 band used for NR can be contiguous in nature. We can use continuous frequencies. So this is how in 3GPP table it is written. DC stands for dual carrier underscore N3AA. So it should be read as that band is band 3. Band 3 is common for NR as well as LTE and AA. AA stands for the number of CCs. So each of the band means each of the technology NR and LTE in band 3 is supporting one carrier. So this is how it is read. So it is contiguous, so it is written as 3AA. If we see this example, when non-contiguous band combination is specified, it is shown as this DC underscore 1A underscore N1A, where first 1A is showing EUTRA band. For this particular case, it is band 1 having one carrier, and the next band after underscore is N1, which is NR band 1, again A, which means number of CCs can be 1. So this is about intraband. Now let us see cases of interband. So interband first category is within FR1. There can be total of 2, 3, 4, 5 or 6 bands. So here we have taken the 6 band case. In this you can see DC is the common prefix. So after DC it is giving 6 bands. 1, 2, 3, 4. Without NR prefix, 4 bands are from LTE and these 2 bands N28 and N78 are from NR. So total of 6 bands, 4 from EUTRA, 2 from NR, each having A as the suffix, which means all of them can have maximum of one carrier component. Next category is including FR2. First one was within FR1 where EUTRA was also FR1 and NR was also FR1. Here EUTRA or LTE layer can be FR1 and NR layer can be FR2. So it is configured as mentioned here. We can see the number of bands. Like in this case, there are total 5 bands. So it can also have possible of 2, 3, 4 or 5 bands. Here we are seeing case of total 5 bands. So 4 bands of EUTRA, band 1, 3, 5 and 7. And similarly last band for FR2NR, which is 257 and 257, and all are having one carrier component. You can see other cases also, like the second case where carrier component for D band 257 is D, means 4 carrier components are supported. Last category is including FR1 and FR2, means LTE is FR1 but NR can be mix of FR1 and FR2. 3GPP has defined similar table for NRDC and NEDC as well. You can refer 38.101-3 document of 3GPP for these kind of details. In this slide, we'll be discussing about the meaning of this attribute in band combination table by 3GPP. Single uplink allowed. What is it? So as we know that we may indicate capability of not supporting simultaneous dual uplink operation with the information element called single uplink transmission, which we have discussed earlier in earlier slides. We know that this is done to remove the possibility of intermodulation interference. When LT and NR transmission collide, simultaneous dual transmission may not be supported by UE for these ENDC band combinations, for which only single switched uplink is supported. So what UE does, for some of the band combinations, UE not support simultaneous uplink transmission. Wherever UE manufacturer feel that there will be intermodulation interference with these band combinations. So there what is supported? Single switched uplink is supported. In this mode, UE uses only one carrier at a time for uplink transmission, either LTE or NR. It is not simultaneous transmission. So UE dynamically switches between them based on the network condition and cell configuration. In the case for ENDC or NEDC configuration listed in tables, like we have seen the example of ENDC, for which the intermodulation product caused by this dual uplink operation may fall into the receive band. Means uplink band, there may be interference due to intermodulation, but there is no interference in the downlink channel bandwidth. In those cases, UE is mandated to operate in dual uplink mode. And how 3GPP mandates that? 3GPP mandates that via this attribute, single uplink allowed. So wherever this single uplink allowed is mentioned as no, there it is necessary, it is mandatory for UE to support this band combination simultaneous uplink transfer. So that is it for this video. Thank you for watching, and I hope that it was worth your time. If you have any queries, questions, do let me know in comment. If you want the video on any other topic or regarding this topic itself, please let me know in the comments. I will try to make the video. And I have taken references from 3GPP and 5G in bullets. This is very good book for 5G concepts. I will share the link in description. If you consider buying it, do check that link. Thank you guys. See you again.